Hi guys, right, I'm talking about working out probabilities from binomial distributions. I just do want to say though, firstly, these questions that I'm only looking at two questions here, but these questions are binomial situations, but I think it's important when you're reading the question that you say to yourself, are they binomial? Is this an appropriate situation for binomial? So does it follow the four conditions of it being binomial? Are the trials independent? That's first one. Is there a fixed number of trials? For each trial, does it end in success or failure? And then is there a constant probability of success? So they're the four conditions that you want. So for example, number 5, if we have a look at number 5, now I think number 5, is that what number 5. I think number 5 is actually quite confusing in the way it's written, really. And honestly, I would say that much of the battle with these questions is taking the information that's written down and interpreting that in the context of trying to get the maths down. So I'm looking at number 5 and it says 95% of his balloons will not burst. I think from reading the rest of the question, it's actually easier to talk about the probability that the balloon bursts, because we want in A, we want none to burst, and in B, we want 2 to burst. So for for the actual situation, I'm going to define my variable. Let X be the number of balloons that burst. I'm writing really funny here, so sorry about that if I keep doing that tonight. Just because of the angle. Right, so how is X distributed? It's binomial. Obviously, that's what we're doing, but it is with parameters 20 and 0.05. So 20 is the fixed number of trials. 0.05 is the fixed probability of success. Okay. So yeah, and just to say, they are independent. Each balloon, there's no reason why one balloon would affect another, really. Okay, so A asks the probability that none of them burst. So that is the probability that X equals 0. Now, I think it's just as well to be familiar with both ways of working that out. So that is like 20 choose 0, 0.05 to the power 0 times 0.95 to the power 20. That's one way to do it. So that's the formula that you use. And remember, this is very reminiscent. I'm going to actually write times there instead of the little dot that I sometimes use. Remember, that I would say this is very reminiscent of the actual binomial theorem from pure maths. So that's one way to do it. The other way is off your calculator. So I would turn it on. Menu 7, and then it's binomial PD. We want the probability distribution of a binomial. So 4, and in this case, the variable, we've got X. We're trying to work out X is 0. N is how many trials there is, 20. And P is the probability of success of each trial, 0.05. Okay, what are we on? 0.358. Now, I would have got exactly the same answer had I have worked it out that way. But I do think it's nice to be fluent in doing both different methods. And then the probability that exactly 2 balloons burst. And here, I am really glad that I decided to let X be the number of balloons that burst rather than the number of balloons that don't burst. Yes, it meant I had a bit of messing around with this probability, but it's meant these are much easier. So again, what would be this calculation? It'd be 20 choose 2 times 0.05 squared times 0.95, weird 5, to the power 18 then. Okay, so they add up to 20. And again, I'm going to work that out on my calculator. I shouldn't have much to do here now. I should only need to change that. Yeah, I'm going to write 2 there equals, there we go, 0.18, 189. Okay, just a little bit of rounds in there. Okay, so that was question 5. Right. And what I would say is that's very standard in terms of having to define your variable, having to say what the distribution is, and then actually working out some probabilities from it. And then one more question that we'll have a look at is, well, just question 7, okay? And question 7, oh, that not working? Yeah, there he is. Right, question 7 asks what I've been going on about. So what assumptions are required? It's important, you'll see, that, you know, that's one way that an examiner will make up marks is, we've got a couple of marks spare. Go ahead, give me 2 conditions where a binomial distribution is appropriate. All right, so independent, fixed number of trials, constant probability of success or failure, and then each trial can only end in success or failure. So that's what you need to say. Those conditions. Right. This one then is more an exercise in setting everything out properly. So again, I'm going to say let X be the number of, what is it? It's people with the genetic marker. I don't really know what that means. People with the genetic marker. Okay. Sounds all very COVID though. Okay, right. So the number of people with the genetic marker is X. So then how is X distributed? Binomial with parameters 50, because that's how many people are in the sample, and then 0.04. I think that percentages are quite a common way of presenting probabilities. I don't love them myself, but it's important to turn it into something that we can actually use there. So like that. And then the question is just asking then, what's the probability that X equals 6? And then, well, you know, let me set it out as we did, using the formula, and then we'll just check it on the calculator as well. So this is 50 choose 6. Then times 0.04 to the 6 times 0.96 to the 44. Okay, I'm going to work that out both ways just to check. So here, X is 6 out of 50 trials, and 0.04 was the probability of success. There we go, 0.0108. Okay, now I will just return to my normal calculator just to check that works exactly. I'm going to type this in. So it's 50 choose 6 times 0.04 to the power 6 times 0.96 to the power. I hope this is the same. Power 44. Right, equals, I want it to be that. Yes, nice one. Okay. Right, so that's all I'm going to say. Once you've mastered working out probabilities in that context, the next thing to do is to work out cumulative probabilities. And I'm just saying one little word about that. That is where there should be X is less than or equal to 6. X is greater than or equal to 6. X is less than 6. All those situations, they're, I'm not going to say more useful, but they come up more often. And the are the answer to more situations. So that's what the next stage of this process is. So well done. Nice one.